In video 6F, we're going to talk about the differences between intermolecular forces, there's going to be 5 of them that we're going to study, as opposed to intramolecular forces. The intramolecular forces is existing within a molecule, and the inter, like the internet, exists between 2 different computers, or in this case, 2 different molecules. The intermolecular forces are going to have a huge effect on our melting points and our boiling points. The intramolecular forces we've already studied. We didn't call them intramolecular forces, but we studied them. We studied them as the bonds. They're either ionic or they are covalent, and they don't have much of an impact on the melting and boiling points. So the 5 intermolecular forces are listed here. London dispersion forces, we'll call them LD forces. Sometimes some books also call them van der Waals forces, just so you don't get confused. Then there's a dipole-dipole force. There's a hydrogen bonding or a hydrogen force. There's an ion dipole force. And then there's ionic forces. These are listed in order from weakest to strongest. I'm going to go into each one individually. The London dispersion force, or the LD force, exists in all molecules. Since all molecules can exist in the liquid and the solid phase, there has to be some kind of force that holds everything together. These are applicable to even the non-polar substances. So what is an LD force? Well, say I have 4 electrons that are being shared here that are floating around between these 2 nuclei in this bond. They're moving around, they're independent of one another. At some point in time, perhaps maybe, all of the electrons are located on one side of the molecule. When this happens, you can see from this picture that the left side gets a little bit larger because it's holding more electrons, and since all the negative charges are on the left, it actually becomes partially negative. If this left side is partially negative, the right side has to become partially positive. That's what's called an instantaneous dipole. The dipole meaning partial positive and partial negative. Why is it instantaneous? Because it only lasts for a split second, and then the electrons are moving in their own independent path again. But for that instantaneous second, where you have a partial positive and a partial negative, it actually attracts a nearby molecule. If this end is partially negative, think of a magnet, it's going to force this end to be if this end is partially positive, it's going to force this end to be partially negative and this end to be partially positive. It's kind of like a domino effect of magnets that can actually change where the electrons are located if you put a magnet up to your molecule. So LD forces are found in all molecules. This is going to be key right here. All molecules, even the nonpolar molecules, because it has to do with where the electrons are located. They are the weakest, again, because it only lasts for an instant. The larger your molecules, so you can look at more mass, more electrons or more mass, the greater the LD forces. So if we look at that on a table, here are 3 examples: fluorine, chlorine, bromine, and iodine. What's happening to their mass? As the mass increases, what happens to the boiling point? 85, 200, 300, 400. As the mass increases, the boiling point increases because these ones down here have a stronger LD force that holds the molecules together. Bigger molecules have greater, stronger LD forces and therefore higher melting and boiling points. Dipole forces. What was a dipole moment again? It has to be a polar molecule. Our bonds have to be between 0.5 and 2.1. It has to be asymmetrical. So now I have these partial positive and partial negative ends to my molecule. What's going to happen is they're going to line up so that each partial negative is surrounded by partial positives. Again, just like a magnet. That little attraction here between the positive and the negative and the positive and the negative adds extra forces that help hold that molecule together. So the dipole-dipole forces, they attract each other, they line up so that all the positive and negative ends are close together. Again, this is pretty weak. It's only 1% as strong as an actual bond because it's just these attractions between different molecules. Because it's very weak, it does not apply to the gases because the molecules are so far apart. So the bigger the molecule, the further apart they are, the weaker this force is. Now this is a little bit stronger than the London force because now I have a set positive and negative. It's not just due to my electrons. I actually have a polar molecule. But it's the second weakest. So when molecules have a similar mass, the molecule with the greater dipole moment, again remember our scale, 0 to 0.5, 0.5 to 2.1, 2.1 to 3.3. The greater this number, the stronger the forces. When you have stronger forces, you have an increase in your boiling point. So here this would be nonpolar. Its boiling point is 231. These guys would be considered polar, polar covalent, 248, 249. And these above 2.1 will be considered ionic. So the higher the dipole moment, the stronger the forces. The stronger the forces, the higher the melting and boiling points. That's dipole-dipole. Hydrogen bonding. Hydrogen bonding is a dipole-dipole force. It has to be between 0.5 and 2.1, and it has to be asymmetrical. Now, what's so special about this? Hydrogen bonding obviously has to have hydrogen. You have hydrogen bonding when there's hydrogen bonded to either a nitrogen, an oxygen, or a fluorine molecule. This is an extra special strong dipole force because hydrogen is so small, it can actually fit into smaller places. And when you're closer together, these attractions here between my partial positive and partial negative are even stronger because they're closer together. So hydrogen bonding will have an effect on the boiling point. These boiling points will be even higher than something with a regular dipole-dipole force because it's stronger than the regular dipole-dipole force. Looking at this chart, you can see H2O's boiling point is 100 degrees. Compare that to H2S, H2SE, H2TE, they're all much lower. If you compare HF, remember hydrogen forces has to have hydrogen with an off, with a nitrogen, oxygen, or fluorine. Here it is with a fluorine compared to a chlorine, bromine, or iodine. Fluorine is much higher. Here it is with a nitrogen compared to a phosphorus or an astatine or an SB, an antimony. Again, still much higher. It does not apply when hydrogen bonds with carbon. Only with oxygen, fluorine, or nitrogen, and of course the hydrogen has to be present. So boiling point increases with increasing size due to your LD forces, but look what happens when you add hydrogen in there, because not only do you have LD forces, you have a dipole-dipole, and you have hydrogen bonding. So you have all three when these are present. Ion dipole forces. These will be easy for you to recognize because you have to have something that's ionic, something that's 2.1 to 3.3, and something that's polar, between 0.5 and 2.1. You must have two substances. These forces exist when you have salt, that's ionic, right, unit 5, in water. Here's my salt. What happens when salt dissolves? Your chlorine becomes a 1 minus, your sodium becomes a 1 plus, and what actually happens when salt dissolves? The water, all the negative chlorines, attract the partial positive of the water. So the waters just surround the chlorine, because it's negative, with their positive ends. The flip side happens with sodium. Since it's positive, this would be like all the oxygens. Since they're the partial negative end, all the oxygens would line up around the sodium. So the positive ion of sodium would attract all the negative parts of the water or the oxygen. Ion dipole forces are stronger than all the other ones, stronger than hydrogen bonding, stronger than dipole, stronger than LD forces, but they're weaker than the very last one, which would be the ionic force. Again, the key to recognizing this, which doesn't come up very often, is you have to have two different substances, something that's ionic with something that's polar. So our last and final intermolecular force is ionic forces. We talked about the big crystal lattice structure of something that's ionic. Again, how are we going to know that in terms of the numbers? It's going to be 2.1 to 3.3. Ionic forces only exist in the ionic compounds. These are the very, very strong compounds. So if this is my sodium-chlorine bond right here, and this is a sodium-chlorine bond right here, they're all going to arrange themselves. Here's my chlorine. Each chlorine is going to surround itself by positive sodium. It's like the little magnets. Ionic substances are very, very strong. They have very high melting and boiling points. They're usually solids at room temperature. This is the strongest of all the intermolecular forces. Not only do I have my ionic bonds, but I have all these extra little magnetic attractions that you would have to break in order to melt an ionic substance. So not only are you breaking the bonds, but you have all these extra forces that you have to get through that big crystal lattice structure in order to melt ionic solids. Here's another chart for you. This will help you determine which intermolecular forces are present in any kind of sample that I might give you. Again, if you want a full-size copy of this, check the Google Docs. You have to ask yourself some more questions. Are there ions involved? If you answer yes, you have to look and see, are there polar molecules also involved? If you have two substances, your forces consist of ion dipole forces. If it's only ions, then you have a purely ionic force as your intermolecular force. If you have no ions involved, then you have to check and see if something is polar. Is it between 0.5 and 2.1? Is it asymmetrical? Answer no. The only possible force you can have is the LD force, the London force. If you do have polar molecules, here's another question. Is there hydrogen also bonded to oxygen, nitrogen, or fluorine? If you see no hydrogen, you only have a dipole force. If there is hydrogen with nitrogen, oxygen, and fluorine, you have hydrogen bonding as well. Again, listed from weakest to the strongest. Questions may ask you, what's the strongest force, in which case you're just picking one. Or it can ask you, list all the forces that are involved in this molecule. If it says list all of the forces, this is present in every single force. So even if you have something that's ionic, ionic forces also have London dispersion forces. An ion dipole force would have ionic forces, it would have a dipole-dipole, and it would have an LD force. Hydrogen bonding, since it is a type of dipole force, it would also have dipole-dipole and an LD force. Dipole-dipole forces would also have LD. Let's try an example. Looking at this list, I know you only have this list, you don't have all the answers. It says, list the following substances in order of increasing boiling point. So I want to look for the weakest and the strongest. If I check out my electronegativity chart, I can see that this, or the fact that this is a metal, automatically alerts me to the fact that this is ionic. Since this is ionic, it must have the highest melting and boiling point. Now I'm going to look for the other end. Something that is nonpolar. There would be two of them. Hydrogen and nitrogen are both nonpolar. So they would only have LD forces. How did I compare my LD forces again? Hydrogen is the smallest. If you look at its mass, it would therefore come first, and then neon would be next. These are both nonpolar. They only have LD forces. C and O, we can look at the numbers, 3.37, and carbon was 2.8, I believe. So this has a polar bond. It's also not symmetrical. So since this is polar, it falls in the middle. LD, it would have a dipole-dipole force, which is stronger. H and F, we don't have to look at numbers here because I can just say, oh, there's a hydrogen with a fluorine. That has hydrogen forces, which is stronger than something that's polar, but not quite as strong as something that's ionic. So, some other similar questions for you would be, given 2 or 3, could you put them in order of increasing boiling points, increasing or decreasing boiling points in terms of their increasing or decreasing strength for the intermolecular forces? Here's our review. This is all of Unit 5. This should say Unit 6. Unit 6 review. All the things you should be able to do for the test. Describe why covalent bonds form. How do you determine if it's ionic or covalent? Are my electrons given, taken, or shared? What will be the relationship between bond energy, strength, and length? Those will be from video A, as well as dipole moments. How does the dipole moment affect the bond strength or the bond energy? Naming ionic compounds. If you need to review this, remember this comes from Unit 5. Naming acids, also Unit 5. And this was the new naming molecular compounds where you use the prefixes. Also in the test, you'll have to be able to compare and contrast properties of ionic and molecular compounds. You'll be asked to draw Lewis structures. You will be asked about the geometry. What's the shape? Is it tetrahedral? Is it linear? Is it bent 1, bent 2? You'll be determining if something is polar or not. Is it asymmetrical? Does it have polar bonds? And then, finally, you'll also be asked questions about intermolecular forces. What are they? All 5. How do they affect boiling and melting points of compounds? And if I give you a compound, you'll have to list which intermolecular force is present in that compound. Write down all your questions. We'll have review when you come back to class.